So today we're going to be talking about colligative properties, and you've probably never heard that word before. Colligative. It's a big word for a simple concept. Okay, how many of you have ever added salt to boiling water when you make pasta? Sure you have. You do it for a couple of reasons. Number one, you do it because the pasta tastes better if you do it. It's really the only way to get flavor into naked pasta. But you also do it because it actually makes the water boil at a hotter temperature. You might think, well, how does that work? Well, that's what we're going to talk about now. So we need to understand that the boiling point and the freezing point of water can change when we add non-volatile solutes to them. And what is a non-volatile solute? Well, a non-volatile solute is any substance that does not evaporate readily at normal temperatures and pressures. So it's something like a solid dissolved in water. So basically a non-volatile solute is any solid we're dissolving in water. A volatile solute would be a gas dissolved in water, or because it means it would evolve out of the water, it would move out, or something like isopropanol, like in the case of isopropyl alcohol, that isopropanol would evaporate faster than the water does. So in a nutshell, non-volatile solutes are basically any solid you dissolve in water. Okay, so when we're talking about the effect of a colligative property, it depends on the number of particles, not the kind of particles we're dealing with. So we're looking purely at concentration, and I'll explain that a little bit more. Okay, it's about the amount of stuff we're putting in the water. Okay, and we'll break that down a little bit as well. So I've said it has this effect. Well, what's the effect? So the more particles you have in the water, and the more those particles dissociate or break apart, because, if you have one particle that you put into the water, one molecule, and it breaks apart into two, well, now you've got more particles in that water because it disassociated, okay? And when that happens, you get a higher boiling point and a lower freezing point. So the boiling point, which for water is 100 degrees Celsius, gets elevated, it gets pushed up. And the freezing point for water, which is 0 degrees Celsius, gets pushed down. So those things that are already extremes, meaning the highest end of the high and the lowest end of the low, they get pushed further out. So your boiling point becomes higher and your freezing point is lower. What's high gets higher, what's low gets lower. Okay, everything becomes more extreme. I'm going to show you some examples of that. So in the wintertime, right, we salt the roads. Not this past winter, my goodness, I don't know that they had to salt them hardly at all. But if we're looking at a normal situation, when you have water, okay, it freezes at 0 degrees Celsius. That's what we call its NFP, or its normal freezing point. It boils at 100 degrees Celsius, which is its NBP, or its normal boiling point. When we add a little bit of salt to that, we can lower the freezing point of that water and we can raise the boiling point. If we add more salt, well, in that case, the effect becomes even more extreme, and we can lower the freezing point even more and raise the boiling point even a little bit higher. Now, you might be wondering, why would you want to do this? Well, if we lower the freezing point of water, and it's water on a road in the wintertime, it actually has to get colder in order for that water to freeze, and it keeps the ice off the roads. Lots of people think that the salt melts the ice. No, 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 it doesn't. Not at all. The salt dissolves into the water that's already there and makes it so that water has to get colder in order to freeze. That's how it works. And with the boiling point elevation, if we add a little bit of salt to our water when we're cooking, that water can actually get hotter than 100 degrees Celsius and thus can cook our food even faster. It's kind of cool. Now, in my second example here, I've got antifreeze. Okay, now antifreeze is a common coolant that you put into your car to keep it from freezing up in the wintertime. Put it used to be back in the day, you put it in your radiator. So if you have plain water, that water would freeze up at 0 degrees Celsius and it would boil at 100 degrees Celsius. If we add a little bit of antifreeze to that water, we can drop that freezing point down to -10. We can raise that boiling point up to 110. If we do a 50-50 mix, you can get an even more efficient spread, and you get a -35 degrees Celsius freezing point, which would take you past the coldest possible day on Long Island, and 130 degree boiling point. So it keeps your cooling system from seizing up. Now let's go back to this salt business on the roads, okay? So if we take sodium chloride, NaCl, classic salt that you think of as salt, table salt, okay? How many particles does sodium chloride dissociate into? NaCl. That's right. It dissociates into 2 particles. So 1 formula unit of sodium chloride would effectively dissociate into 2 ions, a sodium and a chlorine, or a chloride ion, and that would make 2 particles. If we're looking at calcium chloride, on the other hand, CaCl2, well, how many particles is that going to dissociate into? And we talked about this a little bit when we did electrolytes. Well, that's going to dissociate into 2 particles. Sorry, what did I just say? 3 particles. Whew. Gosh, it's been a long week, guys. 3 particles, which means calcium chloride will be more efficient at lowering the freezing point than sodium chloride. And that's why they generally don't put sodium chloride on the roads in the winter. They usually put things like calcium chloride because you get more bang for your buck. Let's do some example problems. So which statement is true when solutes are added to water? Well, our best choice is going to be D. The freezing point will decrease and the boiling point will increase. Everything becomes more extreme. We're pushing to the outer edges. Okay, what's low gets lower, what's high gets higher. Let's try another one. Which of the following sodium chloride solutions has the highest boiling point? So I'm going to give you a little clue. Has to do with concentration. Do you need another clue? Calculate your molarity for each of these conditions. I'm going to pause while you do that. So if we calculate the molarity for each of these solutions, your best choice in terms of concentration would be choice D, because you have 10 moles of sodium chloride dissolved in 400 milliliters of solution. So to get your molarity, you would take 10 moles divided by 0.4 liters of solution. Remember, we always have to convert to liters for that. And you would get a concentration of 25 molar. That would be a 25 molar solution. Pretty darn concentrated. Let's go to another problem. Which of these would have the highest boiling point? Take a moment, answer it now. Your best choice there is going to be choice D. And let's talk through why that is. Choice A, we have a 1 molar solution and we have potassium nitrate. Potassium nitrate will dissociate into 2 particles. 1 times 2 is 2. Choice B, you have 2 molar potassium nitrate. Once again, potassium nitrate dissociates into 2 particles. 2 times 2 is 4. In choice C, you have a 1 molar solution, but calcium nitrate dissociates into 3 particles, 1 calcium, 2 nitrates. So 1 times 3 is 3. In choice D, you have 2 molar calcium nitrate. Calcium nitrate dissociates into 3 particles, so 2 times 3 would be 6. And that would be our combination that would give us the highest boiling point. And let's look at example 30. Which property of distilled water will not be affected by adding 50 milliliters of CH3OH or ethanol to 100 milliliters of water at 50 degrees Celsius? And your best choice there would be conductivity. And the reason for that is that CH3OH, being ethanol, is organic, and it is not conductive, and thus not an electrolyte, and so it will not affect the conductivity. All right, so in our next lesson, we're going to be talking about how we can separate different types of mixtures. Thanks, guys.